How y'all feeling? Quiet nodding, good to see. Anyone need anything or have any questions before we get started? Okay. The main thing we're going to be doing today is starting chapter 4, beginning our discussion of Newton's laws and force. Before that, actually, come on. Put that there. There's computer. You start that over. Oh, weird. Periodically, I just want to make sure that certain upcoming dates stick out in your memory. Today is Monday the 11th, and today we are starting chapter 4. I anticipate spending about 2 weeks on chapter 4. Newton's laws are pretty important. I want to make sure we get a good basis for them. And then about 2 weeks for that, about 1 week for chapter 5. And then to keep this on your calendar, our first test is going to be the first week of October. So we're about a month out. The goal being, we're going to take it over this week, do it during lab. So some of you will have it Monday, Tuesday, Wednesday, or Friday. Lecture will be studying that week for the most part. And then we have fall break for you to have a vacation, and then midterm grades go out on the 13th. So keeping that on your radar. First test will be first week of October on the first 5 chapters of the course. Sound good? And we'll have time to review. I always post a, it's Monday, I'm forgetting English, practice test. I always post a practice test before every test. Even if you don't want to do the whole practice test, you can look at my answer key to see what sorts of questions I'm asking, what sorts of things you should be able to do. And I always spend time in class reviewing before I test. Yes?
Do you have your work on the practice?
I do.
Okay. So we can see how you do it.
Mm-hmm. And the questions will never be exactly the same, but it'll tell you what types of things I'm wanting you to be able to do. And often students just want practice, so I make that as free, completely optional practice. Feel good? Oh, yes.
You said midterm grades are on the 13th?
Correct.
So all homework needs to be done by the 13th?
Ideally, yes. Ideally by the 13th, you will have done all homework and quizzes up through chapter 5. It's not strictly required, but whatever score you have on those assignments will be factored into the midterm. So if you were planning to wait till the end of the semester to do all the homework and quizzes, your midterm grade might suffer for it, but just to make you aware of it. Midterm is just a check-in. It's not like if you're bombing at midterms, it's bad for the whole semester or anything. I do encourage you to do them so that it's a better representation of how you're doing in the course. And they're honestly just good practice for the test. So I do recommend by the time you take the test on this week and before I finish calculating midterm scores by the next week, to have done as much of chapter 1 through 5 homework and quizzes as you can. Any other questions on this particular topic? All right. Well, with that said, do keep that in those dates in the back of your mind. Main article for today is beginning chapter 4 in our study of force via Newton's 3 laws of motion. At the beginning of the semester, I went on a bit of a story. I told a story explaining how Newton's laws were very good, but they didn't explain Mercury's motion, and that's why we thought planet Vulcan existed for about a century. Sound familiar? All right, so Newton's laws, what we're about to study, are the laws that Newton wrote down that were very good and worked for centuries until Mercury was being problematic. They are still good laws, and they work 99.9% of the time unless you're tracking very big motion of very big objects across differences in local space-time. But unless you're doing that, Newton's laws are still very good. That's why we're using them in this class. I do want to dispel the myth that Newton discovered gravity, because, I mean, Newton isn't the person who said, let this happen. Things have been falling for as long as, since before humans were aware things were falling. Things fall, and gravity is our best explanation. Like the written text of our definition of gravity and the formulas for it are our best guess at describing and measuring why that happens. And Newton didn't even invent that. He was not the first person to calculate and write things about gravity. He's just the European that got famous for it. Now that said, what he wrote down is still good and is still very useful, which is why we do still use and talk about it, but he didn't invent gravity, and he was not the first person to discuss these things by a long shot. But let us look at the things that he wrote down and describe them. These are the three laws of motion, and after the motion formulas we've already learned, I would consider these to be the secondary backbone of the course. This course has two backbones. Don't ask me how the biology of that works. That's not my department. And I guarantee you have heard all of these before, and you have observed the phenomena that they are describing before. So the point here is not to give you all new information, it's just to summarize what you already know, and to make sure you can take that knowledge you already know and number it accordingly. So main thing right now is learning which things are associated with which number. I'm going to go over, give a quick read through of these, define some terms, and then we'll start going through them a bit more in depth. Again, you know these, just putting names to it. Law of motion number 1 states that an object at rest will remain at rest, or an object in motion, constant motion, will remain in constant motion until acted upon by an outside force. Law number 2, there is a long paragraph form of it, but the paragraph just translates to this formula. So if I ask you what is Newton's second law, you can just point to that on your formula sheet. If I have some students, when I ask them Newton's second law, would literally just say FMA, and you're not wrong. This law says that the net force acting on an object causes a proportional amount of acceleration. And law number 3, this is probably the one that gets quoted and misquoted the most often. For every action force, there is an equal and opposite reaction force. Do these sound familiar? Very good. Now, before we can use these descriptions in greater detail, I want to make sure to define a few terms with the official physics definitions that we're going to use for them for the rest of the course. First term to define is force. I told you every time we talk about a new variable, I'm going to define it for you, talk about what we measure it in, and other things you need to know about it. So, our first 3 variables were displacement, velocity, and acceleration. This is our next variable, force. And Newton's laws of motion are about force, so we need to define it here if we haven't already done so. So, force, it's a new variable, and anywhere you see a capital F on your formula sheet, it stands for force. It is a vector, and that is because whenever you push anything, you are pushing it in a direction. There is no way to have a directionless force. So all forces are vectors, that'll become important. And the official definition really only says, a force is a push or a pull that acts on objects with mass to create acceleration. This tells us, again, you have to push or pull something, and since it's a vector, that's always in a direction. You have to act upon an object with mass. There is no real way to exert force on things that don't have mass. You can't really exert force on light, for example. And 3, force causes acceleration when acting upon objects with mass. The whole point of force is to push things and make them change motion, is to make them move or make them slow down. Does that sound consistent with your observations? You use your muscles to exert force and cause things to move. You pick things up, you accelerate your own arm, etc., etc. We are going to be measuring force in a new unit called newtons. The unit is newtons, named after the guy, Newton. So, The formulas say F, the numbers will have an N next to them for their unit. And pounds is an alternate unit for force. Odds are you've been thinking of force in terms of pounds your whole life. Anything you would normally measure in pounds can be measured in newtons. And so in this class, things like weight, and I watched a lot of Mythbusters, so they did a lot of explosive force and punching force in pounds. We're gonna do that in newtons, but pounds and newtons measures the same thing. It's just the metric versus imperial unit. For a sense of scale, 1 pound is about 4.5 newtons. So whatever you weigh in pounds, multiply that by 4.5 and you get your weight in newtons. For a further sense of scale, me, fairly average adult human male, I weigh about 1,000 newtons. Just again, for a sense of scale. Feel okay so far? All right. Now, within this definition of force, I have also referenced mass and acceleration. We've defined acceleration already, but I want to make sure that your notes have the definition for mass in them too, as it relates to this particular class. So, mass is lowercase m in your formulas. It is not a vector because you don't ever have 2 kilograms up. You can push something that has a mass of 2 kilograms upward, but the mass itself does not point up. Just the resulting motion points up. So mass is never a vector. Mass does not have a direction. Mass is a measurement of the amount of matter inside of something. We are going to be measuring mass in kilograms in this class. Most metric courses use the base unit for everything, meters instead of kilometers and liters instead of milliliters, for example. But kilograms is kind of an odd exception in physics. Every physics formula I ever give you for this class will be designed to use kilograms instead of base unit grams. And I was never given an official explanation for why physicists decided to do that centuries ago. I assume it's because physicists, at least classically, like Newtonian level physicists from hundreds of years ago, primarily work in terms of, human levels of mass most of the time, calculating the forces that act on bodies and animals and vehicles and things like that. And humans often have masses somewhere between 50 kilograms to 150 kilograms. If we did that in grams, those numbers would be 1,000 times bigger, and so would every number that we calculate based on those masses. So physicists just decided to use kilograms to keep the numbers smaller, as opposed to, say, chemists and biologists who work in grams because they're mostly dealing with cells and small piles of dust. So we use kilograms in here, unlike everyone upstairs who uses grams. Apologies for any incongruities between this and your other classes. For that reason, since we prefer kilograms, the definition of 1 Newton of force is enough force to take a 1 kilogram object and accelerate it at 1 meter per second squared. So 1 Newton is not a small amount of force, really, because 1 kilogram is, I don't actually have a 1 kilogram mass in here. I used to, but someone moved it. This is about half a kilogram, if I'm being honest with you. 1 metal water bottle filled with ice and water. So double this and then chuck it, and that's the amount of force you're exerting. So 1 Newton is not really a tiny amount. You feel 1 Newton of force acting on your body. So, mass, we're gonna measure it in kilograms, not a vector. I'll talk more about this later, but I want to go ahead and address it. Mass is not the same thing as weight. I don't care how much British television you watch. We do not weigh things in kilograms. That's because mass is a measure of the amount of matter inside of something, and weight is a measure of the force of gravity. That means that weight changes if I go to the moon, but mass doesn't. Does that make sense? So for that reason, if I ask you how much something weighs, I'm always going to want force in newtons, not kilograms. Mass is kilograms. It's a quirk of British language that bothers me whenever I'm watching Top Gear or something. But I want to address it because it's an important term. It's an important thing. I'm rambling at this point because I just hate that word. Anyway, questions?
So you said weights in Newton and mass in kilograms?
Mm-hmm.
Okay.
That is because weight is a force, specifically the force of gravity. Questions thus far for these definitions? All right. So with those terms defined, let's look back at the laws of motion and define them and go into a little bit more detail on each of these. Again, you've heard all these before. The first law of motion is commonly referred to as the law of inertia. And what it says is that whatever matter is currently doing, it wants to keep doing. If I was to give this law a name, it would be the law of inertia. And if I was to summarize it very briefly, it would be matter is lazy. Anything made of matter wants to keep doing whatever it's already doing and does not want to change. As an example, behold, matter, a lump of carbon atoms for the most part. I'm going to take this lump of carbon atoms and place it right there. What's it doing? It's not a trick, I promise.
Nothing.
Nothing.
Just sitting there.
It's sitting there. It is currently engaged in constant motion, staying at rest. This object is at rest. And what this law says is that it wants to stay at rest. Is that remote ever completely spontaneously ever going to rocket off on its own accord? No, it doesn't have any moving parts. It doesn't have muscles. It's just a lump of carbon. So it's going to stay there indefinitely until something outside of itself literally forces that to change. I am a being outside of the remote, so I can do this. And that literally forced its motion to change. I used force. But by itself, the remote's just going to keep doing what it's doing, unchanging. It is only when it is forced into a non-equilibrium state that it starts changing. Matter likes equilibrium, it likes to keep doing what it's doing. And that's why things don't spontaneously act on their own. There's always something exerting force, something that is acting to cause the change in motion. Even within your own body, like, you're not really one thing. You're a bunch of different things all stapled together inside of a skin case. So your muscles exert force on your bones and everything else, and that is the force outside of your skeleton that makes your skeleton move. Does that track so far? Okay. Now, this law does have two parts. It not only says that things that remain still want to keep remaining still, things that are moving also want to keep moving. This one's kind of harder to see in terms of what you normally observe in life on Earth, but sorry, I lost my train of thought. I'm mixing my two examples together by accident. When you're driving a car and you take your foot off of the gas, what happens? It keeps rolling. The car wants to keep moving, but eventually it is going to slow down if you leave it on its own. But that's not because the car wants to slow down. The car wants to keep moving. That's why it doesn't just immediately come to a full stop, which is good, because if that did happen, you'd have whiplash every time you left your house. Objects in motion, in constant motion, want to remain in constant motion. And that's why the car keeps moving forward. And it's why the car will remain at roughly the same speed when you turn cruise control on. The reason the car slows down when you take your foot off the gas is because of friction, which is an outside force. It's the force from the road acting on your tires and the wind acting on your chassis, outside of the car itself acting on it to slow it down. So the only reason you slow down is because of an outside force, friction. Which means if friction didn't exist, things could just keep moving forever. And that's why they do that in space. Right now, orbiting this planet, behold, poorly drawn Earth, there is bolts from previous satellites that got knocked off because of accidents, mostly, that are currently orbiting the planet at speed and will continue to do so indefinitely forever because there's nothing up there to stop them. There's no friction, and it's kind of hard to run into them on purpose because it's a big planet and it's a big orbital ring. Until something stops that bolt, it's just gonna go forever because objects in motion remain in motion. I'm going to skip ahead kind of a little bit to the second law here, just to kind of compare the two. If something is not accelerating, net force is zero. And likewise, if net force is zero, you're not accelerating. Constant motion means no acceleration, because acceleration is a change in velocity. If your velocity isn't changing, either because it stays at zero or it stays at something else, you're not accelerating, and net force equals zero. So, any single time you are not accelerating, an object is in equilibrium, and it's going to remain that way until a force changes it. That is true of objects sitting still. That is true of objects moving at constant speed. You don't really see them moving at constant speed that much on Earth, again, because of friction and stuff, but if you throw something into the void of space, it goes forever until it hits something, or the sun incinerates it. There's a semi-famous quote from Mass Effect 2 that I like to bring up. Isaac Newton is the deadliest man in space, because if you throw something, it's going to go until it hits something. Could be thousands of years from now, but if you launch a rocket into space, it will kill something eventually. So, first law, whatever matter's doing, it's going to keep doing until you literally force it to change. This is why it's easier to stay running at the same speed than speed up. Questions thus far? Okay, I ramble about this one for a little bit too long each time. I want to look at the second law now, because since it's a formula, it influences our math, and we do math in this class. Second law states that net force equals mass times acceleration. Therefore, if an object is not accelerating, the net force acting on it is zero. And if the net force isn't zero, it causes acceleration. So looking back at the remote again, if it's not accelerating, it is in equilibrium, and the forces on it all balance out. If I come along and disrupt that equilibrium by exerting force, it causes acceleration. And very specifically, force causes acceleration, a change in velocity. If velocity is not changing, then the force isn't actually disrupting equilibrium at all. Forces cause accelerations, very specifically. Accelerations in objects with mass. And if you want to accelerate something more, you need more force. And if something has more mass in it, it takes more force to make it accelerate. And that's why trucks need bigger engines. It's also why trains are just a big pain to slow down. A lot of mass needs a lot of force to slow it down as well as speed it up. Feel good so far? Okay. I did Taekwondo for about 8 years as a kid, so I tend to reference it a lot in my examples. I may have said this one before, but I didn't learn this in science. I learned this from my Taekwondo instructor. And the way he said it was, if you want to punch harder, you either need a bigger fist or you need to move your fist faster. So that stuck in my head. Might be stuck in yours now. If A equals 0, the net force equals 0. And again, you see that when things are sitting still. But there's another secret facet to this formula. Notice it says sigma F equals mass times acceleration, not just F equals mass times acceleration. I'm going to draw your attention again to my remote. And I'm going to draw what we call a free body diagram to show all of the forces currently acting on that remote. I assume it's like 50 grams. Free body diagram is just a fancy way of saying I'm going to draw a box and put arrows on it representing all the forces that are currently present. Physicists like to draw boxes because we don't tend to be artists. There's a lot of, for some reason, one of my teachers liked to use a lot of cows in examples, and they always were just spheres with spots. But today the remote is a box. So, looking at that remote, what forces are acting on it?
Gravity and the desk pushing it.
Very good. You've already said both of them. On Earth, you can't really escape gravity. If you're made of mass, your mass is going to get pulled towards Earth's core by Earth's mass. So that remote has weight. That is a force. That force should be causing acceleration, right? So why is the remote not accelerating through the table? Because the table's pushing it back up. I am going to tell you that force is called normal force. I will define that formally, if not today, then a day or two. But the table's pushing back. We call that a normal force. And that's true for pretty much anything sitting on a table or in a chair, which is what you guys are doing. These two forces separately do not equal 0. Each of these things on their own is not 0. However, they add up to 0. The net force acting on the remote is 0 because the two main identifiable forces, one points down, one points up, cancel out. You will never not have force acting on you. Even if you leave Earth, there is still force acting on you because technically Earth's gravity never stops. It just gets weaker. But technically gravity goes an infinite distance. You are currently under the gravity of Pluto. It's just very weak because it is very far away. Gravity goes infinitely. When something is not accelerating, it just means all the forces currently balance out and create a state of equilibrium. The forces are there, and they separately don't equal 0, but they add up to 0. Because force is a vector, you have to factor in direction. That is true for objects moving at constant velocity as well, because not accelerating can also mean moving at constant unchanging speed. So if something is moving at constant unchanging speed, all the forces acting on it also equal 0. And that's what the cruise control of your car does. The computer in your engine calculates the barest minimum amount of force required to overcome friction and keep your car in equilibrium. So, net force equals 0 to create no acceleration, because there's always multiple forces acting on things. Anytime you've sat in a chair, your weight pulls you down and the chair pushes up, they cancel out and you remain in place rather than falling through the chair. Same is true for just standing on the ground. Normal force is important because, again, it keeps us from sinking through the earth and burning up in Earth's core. Okay so far? All right. So this is the main formula we use to calculate force. Very specifically, net force causes acceleration. not individual forces. The net force has to be imbalanced to create an acceleration. I'm just going to go over the last law very briefly. It matters the least to our math, but it'll come up in a few places moving forward. For every action force, there is an equal and opposite reaction force. The normal force from the table on the remote is related to that because the remote pushes into the table pushes back up on the remote. That's where that force comes from, and it's why the remote is able to remain in place. Same as, again, true of you anytime you stand on the ground or sit in a chair. Any force always creates an opposite, and I mean every single one of them, literally. If I lean against the wall pushes on me, and that's why I don't fall through the wall. And I do mean every single force, and that's why punching things hurts. If you exert force on wall exerts force back on your knuckles. Now, if you break whatever you're exerting force on, it means that it wasn't able to exert enough force back to stop you. Say I punch with a force of 50 newtons and a piece of wood can only exert a maximum of 10. It'll exert the 10 on my hand, and it'll only take 10 of the 50 I can push with to break through the wood. And as a result, that hurts less than if I punch stone, which can take all 50 and stops my fist in its tracks and hurts. So if you break something, that means you overpower the force it can exert back. And it means you didn't have to exert all the force you were trying to exert. But every force always creates an opposite. I mean literally every single one of them. Even gravity creates an opposite force. The opposite of Earth's gravity on you is secretly your gravity on Earth, because all mass has gravity, including humans. Again, this one will come up the least often, but I'll describe it when it does come up. I feel. Questions thus far? All right. One of these laws is a formula, so let's do a little bit of sample math before we call it for today. Got about 2.5 questions here to use the principles we just talked about. Using a baseball bat, you strike a 50-gram baseball with 100 newtons of force. What will the ball's resulting acceleration be? Secretly, the function of most human tools and sports equipment is to exert force on things. What kind of answers you guys get? As per my usual habit, I created a picture, I listed the variables that we have and the one that we want. What one formula contains all three of these things? I'm not tricking you. Newton's second law, net force equals mass times acceleration. So, all we really need to do is plug in 100 for force and 50 for mass. Then we should be good, correct?
Don't we need to like convert?
We do. Very good. That was a small trick. As I said, we like kilograms in this class. So you should begin mentally training yourself. Every time you see grams, your brain needs to auto-convert it to kilograms. And that is again because the formula is designed to take kilograms because the definition of 1 Newton is the force required to accelerate 1 kilogram at 1 meter per second squared. So how many kilograms is 50 grams? 0.05, very good. This is the effect of dividing by 1,000, or using the visual method, dragging decimal place 3 spots to the left. So instead of 50, you want to use 0.05. If I haven't mentioned it yet, I usually put a 0 in front of the decimal point just to make the decimal point easier to see. So that's why that's there. You don't have to do it. I just do it for really my own benefit. And now that we've converted, we'll get the actual acceleration. About 2,000 meters per second squared. Now, sometimes the examples I write don't match up reality super well. I don't have the massive baseball memorized to start with. If this actually happened, the baseball might break Mach 1, maybe, assuming it's in contact with the bat for at least a third of, even a sixth of a second, if I'm honest. So that's either too much force or too small of a baseball. So this would be what happens if you ask the Hulk to play on your Little League team. But, math feel okay? All right, again, get in that habit. Anytime you see grams, you want it to say kilograms. Next, we have a 2,000 kilogram car, which is, just for a sense of scale, about the average mass of an SUV, somewhere between a sedan and a truck. And it's already in kilograms, which is nice. Driving at a constant velocity of 30 meters per second. And we want to know the net force acting on that truck. So, how do we proceed? Good catch. Anyone else see that? Our new formula is net force equals mass times acceleration. What is the acceleration of a car that is moving at constant velocity? 0. Very good. Doesn't matter how fast you're already moving, if your speed doesn't change, you're not accelerating. You're just continuously going fast. And to prove this mathematically, the definition of acceleration is delta V over delta T. If we're moving at 30 and we stay at 30, delta V is 0. Therefore, A is 0. Therefore, no matter how heavy this truck is or how fast it's moving, if it's moving at constant speed, and therefore A is 0, net force is also 0. Again, this happens for any object moving at constant speed. And any object sitting still. Related question. We're going to draw a free body diagram of a truck. Behold the new Nissan Box. What individual forces would be acting on this particular object?
Gravity, normal force, applied force, and friction.
Very good. Since there's a lot of individually named types of force out there, there's going to be a lot of times where F has a subscript describing what type of force it is. So I'm going to talk about a few common options briefly. Here we have 4 different forces acting on this truck that are all adding up to 0 to create the lack of acceleration we're currently noticing. They are all force, they are all measured in newtons, they are all the same type of thing. They're just caused by different sources and pointing in different directions. But they're all still force, they're all still measured in newtons. To describe each one, if you, again, compare this to a vehicle on the road, assuming you're driving on planet Earth, there will be a force down caused by Earth's gravity. So Fg will stand for force of gravity. That is a synonym to the term weight. Weight is force of gravity, and it is measured in newtons. It is not the same thing as mass. So, assuming that an example takes place on a planet, there's always a force of gravity down. Now, why does the truck not fall through the earth? 2 people muttered it. Yes, the road is going to push back up. And we refer to this phenomenon as normal force. The act of a surface pushing back out against you, we call that normal force. And it's not because this force is, say, typical normal. We call it that because of the mathematical definition of normal. Because to mathematicians, normal is a synonym to perpendicular. Normal forces point perpendicularly out of whatever surface creates them. So if you are sitting or driving along flat ground, the ground pushes up perpendicularly out of itself to keep you from falling through it. And that's where the name normal force comes from. What it means in this case is just the ground is pushing up, preventing the vehicle from falling through it. And as a result, these 2 things cancel out and the vehicle does not accelerate up or down. Sound okay? All right, I'll make sure this definition feels good in the coming days. We're going to be using this term a lot. Yes?
The net force is just the force acting on the object, because even though it's 0, it would still have force if it hits something.
Well, the collision would be a separate interaction. If it's driving on its own, these would be all the forces present and they would add up to 0. As soon as you hit something, you're adding a new force in. And that's probably not balanced. That will cause an acceleration of slowing from 60 to 0 in 0.2 seconds. So hitting something introduces a force that's not already here. Does that answer the question? Okay. So right now, still driving at constant speed. Gravity down and normal force up tend to cancel out, and that's why you remain on a surface rather than falling through it. If you do sit on something and fall through it, it's because it didn't exert enough normal force to negate the weight of whatever you placed on it. The other 2 forces here are FF, which I'm going to use commonly for force of friction. It's going to come up a lot. We're going to define it later. But for right now, the thing to know is that friction always opposes motion. It's always there to slow you down. If the truck wants to move forward, friction is going to point backwards. It's always trying to slow you down, and it's why the car will eventually stop when you take your foot off the gas. If you want the car to remain at constant speed, you have to very lightly push on the accelerator and generate enough applied forward pointing force to negate friction pointing backwards. And that's what cruise control does for you. So, at least 4 forces are present on this vehicle, and for it to remain at constant speed, they all have to point in different directions and add up to 0. This happens anytime something is not accelerating. This is also commonly called equilibrium. If something's in equilibrium, it's going to keep doing whatever it's doing forever until the equilibrium breaks. How you guys feel? All right. As the week goes on, we're going to do more examples of calculating forces using these formulas and describing more types of force, formally defining them, talking about the different types, where they come from, different formulas for each, to make sure you're comfortable with all the different types and how they affect our lives. Questions for right now? All right. In that case, we'll call it here for today. Report to lab as normal this week. This week's lab is Cannons Part 2. Let me know if you need anything, if you're working on your homework. Quick question that I meant to ask at the beginning of class. Do any of you intend to continue on to Physics 1510 next semester? Show of hands. Okay. Three. Thank you. That is just department information that we need. Thank you. Have a great day.